We are given with this differential equation, and it is claimed to have repeated imaginary roots pertaining to its equivalent auxiliary equation. And then if we were able to verify that, we're going to use the specific process of providing the solution for this kind of situation. But first, of course, let's try to solve this. Let us try to come up first with an equation using the differential operator d. Of course, it would be in y equal to 0 because y is your dependent variable here. That would mean the form of this equation would be 16. That's d to the power of 4 plus 24 d squared plus 9 multiplied to y is equal to 0, which will then be created or followed with our auxiliary equation here where we use m. So you have 16 m to the power of 4 plus 24 m squared plus 9 equal to 0. Okay, now we are going to solve for the roots of this given equation now, so and verify if they are imaginary and if there is a multiplicity. Now, there are a lot of ways to solve this or solve for the roots, but I would like us to use this process because we can see a certain factor that can be substituted here, like this. If we have let k be equal to m squared, what would happen now for this equation would be 16 k squared, because m to the power of 4 is m squared times m squared. So there are two k's. Then plus 24k plus 9 is equal to 0. So it's now easier to look at this because we now have quadratic equation. But of course, let's not forget its equivalence here. At the same time, we can actually see here that this given is actually, or this quadratic equation now is a perfect square trinomial. Perfect square, and the middle term is twice the square root of the first term, 4k, times the square root of the third term. We have 2 times 4 is 8 times 3 is 24k. That means our equation here is a perfect square trinomial. Hence, we can simply factor out, take the square root of the first term. You will have 4k, square root of the last term, 3, the sign of the middle term, plus square of that. That's the factor of our given quadratic equation now here. This would be our roots now. 4k plus 3 times 4k plus 3 is equal to 0. So our first result here is 4k plus 3 is equal to 0. You also have here 4k plus 3 is equal to 0. No need to do this because we have the same results here, and that means the repetition or multiplicity is already verified here. But of course, you will have here 4k is equal to what do you call this one, minus 3. So k is equal to negative 3/4, right? K is equal to negative 3/4. But what was k here? Again, it should also be the same value here, minus 3/4. But what was k? K is m squared. Now, we can return to m squared, stating m squared is equal to negative 3/4. Then, we take the square root of both sides. M is equal to plus minus the square root of negative 3/4. Applying the laws of radicals, you have square root of 3 over, or you can do it like this, square root, that's negative 3 square root of 4, which will give you a plus minus, you will have here square root of, let's start with the denominator, that's actually 2, okay? Plus minus, now you will have this is actually square root of 3 times square root of negative 1 all over 2. So your final roots are plus minus square root of 3i over 2. Okay, square root of 3i all over 2. In short, if our roots are in this form, a plus minus bi, our a here is just 0, and our b is square root of 3 halves. Okay? Square root of 3 halves, because that's what is paired here, bi. So we're talking into this because we know that this is with multiplicity of 2. Okay, so we have now verified the presence of imaginary. Earlier, we have verified repetition. Hence, we'll be using the solution intended for this type of situation. And a solution can be expressed in this manner. Your solution will come into this form. You will have y is equal to, you will have your e to the power of ax times c sub 1 cosine of bx plus c sub 2 sine of bx. That's for your imaginary. But since there are repetitions, you'll have plus, you include x here, e to the power of ax. Your a is the same because it's repeated, as well as your b. No, this would be c sub 3 now, and c sub 4 because we have used already c sub 1 and c sub 2. Sine bx. Then plus dot 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 until you reach x n minus 1 e to the power of ax times c n plus 1. We're just looking into this general form. Cosine of bx plus c sub n sine of bx. But since our repetition is only with multiplicity of 2, so we'll just end up in this form. So our final solution is in this form. Y is equal to e to the power of 0x, that's your a, times c sub 1 cosine your b is actually square root of 3 over 2. So please do not forget about that. You will have square root of 3 over 2x plus c sub 2, sine square root of 3 over 2x. Okay, plus you will have your x e to the power of 0x as well. Then you will have here times c sub 3 cosine of same square root of 3 over 2x plus c sub 4 sine square root of 3 over 2x. Okay, so we have this our solution. But of course, you can improve that knowing that this is just equal to 1 as well as this. So you can simply remove that, and let me remove this, remove the grouping symbol. Okay, remove this here and write it closer to one another. Okay, the x is still x there, only the e to the power of 0 is just equal to 1. So you have here plus x with this, and this is actually again the solution for the given equation. Y is equal to this form here. Thank you very much for watching.